In this presentation, I'm going to describe a new reactor concept that we have developed. This reactor exhibits some unique properties. The conversion in this reactor is not limited by the same chemical equilibrium considerations as a conventional reactor. And as a consequence of this, the reaction products can be produced as pure separate streams. The key to the way this reactor operates is its memory, and we have thus named the reactor a memory reactor, or here a hydrogen memory reactor, as we select hydrogen production to demonstrate our approach. My name is Ian Metcalf and I'm the lead author of the paper. Now, the most efficient way of performing any process involves operating it in what is known as thermodynamically reversible way. And we probably all know that thermodynamic reversibility is only achieved if we have very small driving forces in our process at all times. However, chemical reactors, at the heart of any chemical process, have always been irreversible in nature. Today, I'm going to show you how we have developed a thermodynamically reversible chemical reactor. As I have mentioned, the conversion in this reactor is not limited by the same chemical equilibrium considerations as a conventional reactor, and the reactor can produce pure, separated product streams. This work is the result of a collaboration between Newcastle University, Durham University, the University of Edinburgh, and the European Synchrotron Radiation Facility. The water gas shift reaction is an important step in industrial hydrogen production. This involves the reaction of water and carbon monoxide to produce hydrogen and carbon dioxide. This is a reversible chemical reaction. This reaction is equilibrium limited. In fact, as a reference point at about 810 degrees C, the Gibbs free energy change for the reaction is zero. This means that the equilibrium constant is unity, which means that any conventional reactor will produce a mixture of carbon monoxide, carbon dioxide, water and hydrogen in the product stream. Here we show how a conventional water gas shift reactor operates. Water and carbon monoxide are fed to the reactor, which is packed with a water gas shift catalyst. If a one-to-one mixture of water and carbon monoxide is fed to the reactor, thermodynamics tells us that a one-to-one mixture of carbon monoxide to carbon dioxide to water to hydrogen would be produced. So clearly further treatment is required to get a pure hydrogen product. Now, hydrogen can also be produced using what is called a chemical looping process. Here, the catalyst is replaced by an oxygen carrier such as a metal-metal oxide system. The role of the oxygen carrier is to transfer oxygen from the oxidizing water stream to the reducing carbon monoxide stream. Now, if we're going to move oxygen around, we need a scale to represent the oxidizing potential of the gases and solids we're going to work with. And we use colors to do this. Red is the most oxidizing, and blue is the most reducing. Our most oxidizing gases are water and carbon dioxide, shown as red. Our most reducing gases are hydrogen and carbon monoxide, shown as blue. Oxides of carbon are differentiated by having a black border. In the case of gas mixtures, we can have intermediate oxidizing ability. So a mixture of red and blue molecules in oxidizing terms can be orange, or lighter blue if the proportion of reducing molecules is greater than oxidizing. Now let's think about how our metal-metal oxide system behaves. Here we show a figure of the oxygen content of the system versus oxidizing potential. If our oxidizing potential is low, the blue colors, we have a metal. This has low oxygen content. If our oxidizing potential is higher, the orange and red colors, we have a metal oxide, and the oxygen content of the solid is much greater. Notice that we can effectively represent the metal as light blue and the oxide as orange, as the phase transition lies between these two colors. We don't need the whole palette of colors. Now look at what happens if we use such a material in a chemical looping process. Let's start with the reduced material, that's light blue, and we expose it to water, remember that's red, and the water will start to oxidize the bed. The product exits over a reduced light blue bed, and if there is thermodynamic equilibrium between gas and solid, the gas must be composed of a mixture of red and blue, water and hydrogen molecules. It cannot be all blue, as our solid is not reducing enough. Pure hydrogen cannot be produced. The graph at the top of the bed shows the hydrogen-water mole percentage leaving the bed. And you can see that this composition never changes until the bed is completely oxidized by water. At this point, we need to regenerate the bed, and we do this with a reducing gas such as carbon monoxide to produce the metal again. It makes sense to feed the reducing gas from the opposite end of the bed to the oxidizing gas. This is known as countercurrent or reverse flow. Here, the metal is formed once again by a reaction of the oxide with carbon monoxide to produce metal and carbon dioxide. But again, note that the carbon dioxide is always produced with some carbon monoxide. Once more, this composition does not change with time until the bed is exhausted. Now we could change the metal-metal oxide system to favour, for instance, higher conversions to hydrogen. This would require a phase change that occurs at a low oxidizing potential and so can achieve a higher hydrogen to water ratio in the product stream. However, on reduction in carbon monoxide, poor conversions will occur as the phase transition is not sufficiently oxidizing to produce much carbon dioxide. We could change the metal-metal oxide system to favour, for instance, higher conversions of carbon monoxide by choosing a more oxidizing phase transition. But of course, this would lead to poor water conversions. So using such systems, we can never have a material that gives us good conversions to hydrogen and to carbon dioxide at the same time. So we have a problem, as we will have to perform separations after the chemical looping process. But could we do better? I'm going to show you that we can. Thermodynamically, we run into problems here because we have an oxidizing feed and a reducing feed. However, we must choose how oxidizing the phase transition must be. As we only have one phase transition, there must always be a large driving force, thermodynamic driving force, for oxygen exchange between the solid phase and at least one of the feed gases. This leads to an irreversibility. Remember that driving forces must be low at all times for reversible operation. Our solution is to use a special kind of material as the oxygen carrier. This is an oxide of variable non-stoichiometry. Here we show a figure of oxygen content versus oxidizing potential for such a material. And for this class of material, we see that the oxygen content varies continuously with oxidizing potential. There is no phase change as such. So whichever gas composition we expose the material to, it will always have some oxygen available. The material itself can exhibit oxidizing potentials all the way from blue to red. It is not limited to a narrow range of oxidizing potentials like a metal-metal oxide system. Now look at what happens if we use such a material in a chemical looping process. Let's say that we start off with a reduced material, and this would be blue, and we expose it to water, remember that's red, and the water will start to oxidize the bed. This must be irreversible at first because we have red molecules hitting a blue bed. However, the product exits over a reduced part of the bed, which is blue, and so will be almost entirely hydrogen if there is equilibrium in that part of the bed. There will be no water present in the outlet stream. In fact, the outlet composition will not begin to change until the reaction front in the solid phase has moved right through the bed and the oxidizing potential of the solid right at the outlet starts to change. Then unreacted water appears and the conversion eventually drops to zero and the reaction front is completely lost from the bed. The bed is now oxidized and it's become red. We reduce the bed with carbon monoxide and once again, because the bed begins as fully oxidized, we produce pure carbon dioxide. This continues until the reaction front starts to affect the outlet composition again. And eventually, the bed is completely reduced and pure carbon monoxide exits. However, if we shorten the duration of the half cycles, such that the profile of oxidation states is not fully removed from the bed, we can operate the reactor in a manner approaching thermodynamic reversibility. Cycles are short enough that one end of the bed is always oxidized and one end always reduced. One end is always red and one end is always blue, and hence the term memory reactor. The reactor bed remembers the oxidizing potentials of the feed gases that it is exposed to. The capacity of the bed comes from the small shift back and forth of the oxidation state profile. Essentially, pure products are always obtained, and thus overall water-gas shift equilibrium limitations are overcome. The bed does not, of course, violate thermodynamics. Equilibrium can be overcome because the water and carbon monoxide feeds are never mixed as they would have been in a conventional reactor. So pure hydrogen and carbon dioxide are obtained from the two different ends of the bed. But of course, we need appropriate switching valves, which I haven't shown here, to capture the products for use. And any real process would be likely to use a syngas feed of carbon monoxide and hydrogen as the reducing gas. And so it would look slightly different in that there would need to be a separation of water from the carbon dioxide product. But that's a very easy separation. Now in this paper, we will operate a real water-gas shift reactor at high conversions to hydrogen and carbon dioxide. We will use a lanthanum strontium ferrate non-stoichiometric oxygen carrier. Furthermore, the bed was operated at the European synchrotron radiation facility in order to perform spatially and temporally resolved X-ray diffraction to show that the bed retains this profile of oxidation states or memory within it. To do this, we use the principle that when a non-stoichiometric oxide loses oxygen, it expands slightly. This means that the lattice parameter of the oxide increases, and this can be observed with X-ray diffraction.